Up to this point, all of the model evaluation measures we've looked at assess predictability in the sample data used to build the model. And that's great, but these measures don't help gauge how well an estimated model predicts an unseen sample. It is entirely possible that a model will perform well with the sample, but then perform poorly with a new sample. Overfitting is an issue that pops up when an estimated model describes the sample data rather than the relationship between the variables in the model. So we need a measure of the predictive power of a model based on a set of data not used in estimation. In walks our new friend, cross-validation. Cross-validation evaluates predictive models by partitioning the sample data into a training set and a validation set. The training set is used to build the model, and the validation set is used to evaluate or validate the model. It's common to use the root mean square error on the validation set or the accuracy rate when evaluating binary choice models. One method of cross-validation is the holdout method, which partitions the sample data set into two independent and mutually exclusive data sets. The method is implemented in 4 steps. The first is to partition the sample data into 2 parts, training and validation sets. Next, you use the training set to estimate competing models. Then, use the estimates from the training set to predict the response in the validation set, and then calculate the RMSE for each competing model. Ultimately, the preferred model will have the smallest RMSE. This approach is fairly straightforward and can be done by randomizing the order of your observations and then dividing them into 2 groups. Though a limitation to this approach is that the experiment is only performed once. But sometimes model selection is sensitive to how data are partitioned. K-fold cross-validation partitions the sample data into K subsets, and K-1 sets are used for training, and the remaining set is used for validation. And the greater value that K takes, the more reliable the result, but the more computationally intensive the experiments are. The average of the assessment measures is used to select the best model. What is illustrated on this slide is that we can experiment and partition data as frequently and in as many ways as we would like. So it is more likely to find the best model using the K-fold method, even though it tends to be more computationally intensive. And you'll have opportunities to practice each of these methods as this class continues.